Welcome, everyone, to our webinar on decarbonizing chemical production, innovation strategies. My name is David Hart. I'm the director of the Center for Clean Energy Innovation at ITIF and a professor at George Mason's Schar School of Policy and Government. ITIF, for those of you who aren't familiar with it, is a nonpartisan, nonprofit think tank based in Washington, D.C. that covers a wide range of science, technology, and innovation policy issues, both in the U.S. and globally. The webinar is hosted by my ITIF Center, along with Mason's Center for Energy Science and Policy, and our partner at the regional level, the Center for Houston's Future. At this webinar, we're going to share the results of a year-long project that we are in the midst of publishing. The products of that work include a report on the PVC value chain, which you can find on the Mason Center for Energy Science and Policy and the Center for Houston Future's website. I think you'll find it easily by using the keyword PVC. And Ron Whitfield is here to discuss that. I've also produced a report for ITIF, which I'll talk about. And soon we'll be publishing a report on advanced technologies for decarbonizing chemical production, which Henry Kelly will talk about. Breakthrough Energy was a major funder of this work, and we're very grateful to them for that support. And I'm really pleased to welcome Abigail Rajitsky from Breakthrough to moderate today's session. Before joining Breakthrough, Abigail worked on Capitol Hill. Most recently, she was with the House Select Committee on the Climate Crisis, and she helps to lead Breakthrough's work on industrial emissions. Abigail, thanks for joining, and leave it to you to chair the session.
Thanks so much, David, and welcome everyone. Thanks so much for joining us. So I'll do some quick intros of our speakers and then get you to the presentations that you're here to see. So first, we're going to hear from Ron Whitfield. He is the lead author of the PVC Pathway Study. He's executive professor and founding director of the Business Sustainability Initiative at Northeastern University's Business School. And he is a longtime consultant in the chemical industry and an economist by training. After Ron's presentation, we'll hear from David, and then we'll hear from Henry Kelly, who is the author of a soon-to-be published work on advanced technologies for chemical industry decarbonization, which he will talk about today. He's the former senior official in the Department of Energy and at the White House Office of Science and Technology Policy, among many other roles, and has his PhD in physics. So with that, I'll turn it over to Ron for our first presentation.
Well, thank you very much, Abigail. And it's a pleasure to be here today. My role is to give you a quick summary of the PVC study we recently completed. So I'm going to jump right in and give you some background first. The petrochemical industry is one of the most challenging industries in the economy to decarbonize. It's extremely complex. It's capital and energy intensive, and it's considered one of the hardest to abate industries, along with iron and steel and cement. We have chosen to analyze in depth one major segment of the industry, since that's easier to understand and we can get into greater depth in just one segment. Our goal in this analysis is to demonstrate how this single value chain can achieve near net zero carbon emissions by 2050, with maturities approaching maturity today at a relatively well-documented economic cost. Now, why do we choose PVC? First, it's a large industry, big production, a lot of dollar sales, many workers, thousands of workers. It's also a very large emitter of CO2. So if we move the needle on this one, it actually moves the needle for the whole industry. The US is arguably the lowest cost producer of PVC and its intermediate products in the world, which means it's the large exporter of PVC and the intermediates in the world. It's number one. Now, one could ask, what differentiates PVC from other larger polymer chains? Why didn't you pick some other ones? Well, the two largest polymer chains are polyethylene and polypropylene. This is a little bit of background. Both of these polymer chains or polymers produce largely single-use applications, packaging, straws, bottles, etc. PVC, on the other hand, is going primarily into highly durable goods, such as building and construction, underground pipe, and things of that sort. A pound of PVC produced today, as revealed by our research, can be expected to remain in use for an average of at least 37 years or more. Now, one could ask what makes our study unique? By focusing on just one value chain, we can go very deeply into the workings of this value chain. So our estimates draw upon a bottoms-up model of the PVC value chain, which represents every single plant in the US that contributes to PVC production today. The diagram on the slide shows the extent of this value chain within the system boundaries we've chosen. The two major raw materials are called chlorine and ethylene, which most of you are familiar with. And we've also included in this value chain the combined heat and power plants that provide the power and steam for this very large and capital intensive and energy intensive industry. When you combine chlorine and ethylene, you produce intermediates, EDC, which is the chemical name is ethylene dichloride, or VCM, vinyl chloride monomer, and that goes directly into PVC resin. And that goes into siding and pipe and vinyl records, etc. Now, what are some of the benefits of actually going this route, which is a little different than most other studies we've seen? First, it avoids the use of industry averages. This is a very diverse and heterogeneous industry. And by going deeply, we can uncover the differences in scale. Large plants versus small plants, old plants versus new plants. Also, differences in technologies. For example, some of you may know that chlorine can be produced either with a diaphragm cell or a membrane cell. One is more energy efficient, one is less energy efficient. We can identify those plants that would use one technology versus the other one and capture that in our modeling work. The next major difference is feedstocks. The ethylene chain has many different feedstocks. And of course, the last item which makes us different is we can capture the clustering effect if plants get integrated properly and most energy efficiently. The next major benefit, which we consider to be important, is by focusing on this well-defined and diverse set of assets, we can evaluate capital investments in new carbon reducing technologies at each site in each time frame, using a simplified corporate financial model that weighs the investment cost of the technology against the environmental benefits of using the technology. In doing our research, we went back 30 years in order to look at the next 30 years. So we used 2020 as sort of the base year. And going back to 1990, we saw many plants back in 1990 were a fraction of the size of plants today. And if we're going out to 2050, we think that the next group of plants that get expanded will have to be more energy efficient and replicate the most efficient plants we have today. This rate of growth in PVC, which grows in our projections from 10 million metric tons to 16 million metric tons of PVC equivalent production, is a moving target for decarb policies. As higher production is required, we allow the model to add new plants that are modern and energy efficient and replace or upgrade plants at the end of their useful life. By doing this approach, we have a certain baked-in carbon intensity improvement over the next 30 years, although not nearly enough to meet the climate goals of 2050. So in doing our research, we first screened many technologies, and we looked at many different ways of decarbonizing this value chain. We talked about bioethanol, ethylene from bioethanol, hydrogen production from ATR with carbon capture and storage, electrifying the boilers, and also carbon capture and sequestration, which is applied in other industries. There are also many other disrupting technologies that are out there, which are being demonstrated in various stages of demonstration. E-crackers, chlorine-free gas to produce ADC, replacing the entire front end of the PVC chain with acetylene. So we screened these technologies and came up with three major criteria for rapid decarbonization of the PVC chain. The first is timing. We don't think we can wait very long. So there's an urgency of climate change, and that was one of our major criteria. which technologies are readily available soon rather than later to decarbonize this industry. The second is scalability. We talked about the size of this industry. It's big. So we have to be able to scale up technologies that can decarbonize at a rate which has got to be very rapid. We can't wait forever to scale up these technologies. And the third criteria we chose was economics. In order to do this investment analysis, we have to have realistic cost projections. And small lab scale technologies are very difficult to scale up and also get reasonable cost projections. So those are our criteria. And after the screening step was over, we decided to explore two major pathways in detail. Neither one of them are perfect, and neither one are available yet, but they're going to be coming soon, in our opinion. Those two technologies are carbon capture and sequestration and hydrogen. Other technologies are certainly out there. They're being developed, they're being tested, they're being demoed, etc. And they may be game changing. We just can't be sure about that. And of course, our assumptions about the economic growth and energy prices could change dramatically over the forecast horizon. And that could encourage or discourage some of these technologies. So I want to make sure that that's clear. So let's talk about some of the highlights of the study. The major highlight is both of these technologies, CCS and hydrogen, can achieve between 80 and 90% reduction in CO2 emissions compared to the base year by 2050, which is a pretty darn good achievement. The only difference in these technologies, and they converge in 2050, the only difference in the model outcomes is the steepness of the path, the trajectory. More aggressive policy actions, and David will talk about this later, can accelerate the downward trajectory. The trajectories themselves were calculated using our discounted cash flow model with the price of carbon as the driving force. Higher levels of abatement above the 80-90% level could be achieved if the electric power grid were decarbonized more quickly than projected in the official forecasts. So that's one of the major takeaways. The second major takeaway is the green premium. How much will this cost? We have decarbonized the value chain, and it's going to cost a significant amount of money. In economics terms, there's no such thing as a free lunch. By allocating, we have to allocate because, as we mentioned earlier, chlorine and ethylene have other uses besides just PVC. So after allocating the increased cost against only the PVC production, which is going to be 16 million metric tons in 2050, the industry average incremental cost for low carbon PVC is on the order of 10% plus or minus 5% based on the scenarios. That's 10% on the price of PVC in 2020. This is what we calculate to be the green premium, and we can get into the actual calculations in the study. But that's a major finding, that it's not going to be so high that it can't be dealt with in practice. So in time remaining, let me give you some final comments. The green premium, I mentioned PVC production can't be decarbonized without substantial costs. More than half of the costs are being borne by the chlorine and ethylene derivatives coming out of our value chain. So we have to consider that this is a concern and an uncertainty. There's also uncertainties about the delayed infrastructure development. We can't have CCS without carbon, without transportation of CO2 and sequestration sites being identified. We also can't achieve these goals without hydrogen transportation. And there's lots of effort, as most of you know, in developing the infrastructure for these, including some of the bills passed by the recent Congress. There are also uncertainties about the site-specific constraints on the technologies. Will there be enough real estate? Will they be able to adopt these technologies given the site constraints? And of course, there's always supply chain resources for project execution. It goes without saying. And the third kind of final comment is we need intelligent public policy and regulation. The scenarios use a carbon price as a proxy to drive the financial model. It's a simple proxy, but it's not the only policy options that should be considered. And I'm sure David will talk much more about other policy options. So just to wrap it up, if the bottoms-up approach can work for PVC, can we apply it more broadly to other petrochemical value chains? That's sort of one of our goals, was to do this as a pilot. And the second major question is, are there other technologies that we should think about? Is there enough information out there to do them justice? So thank you very much. And I will now turn the podium over to the next speaker.
David, I think you're muted for the audience here.
Thank you. Take care of that. I appreciate that, Abigail. Thank you, Ron. You set me up very well for this. And I feel like I learned a ton on this project, just enough to be dangerous. And it's very important as we think about the policy implications to temper them, because it is a first pass. It really needs to be validated, and there's a lot more work to be done. But I do think it provides some insights that may be useful for studying the industry as a whole. And as Ron mentioned, the study uses carbon price as a proxy for public policy, but what we really need is a package of policies. So I'm going to talk through a series of policies that would be useful in this industry, that we studied, perhaps other value chains, as well, over a series of timescales, starting with things that we can do right away, funding demonstration projects using funding that's already been allocated, all the way out to the stage in which these technologies would need to be widely adopted across the whole industry, which would involve carbon pricing or pollution regulation. And you can think of these various timescales as decades, perhaps the first group in the 2020s, the next in the 2030s, and the last ones perhaps in the 2040s, depending on how quickly the infrastructure and some of the other supporting requirements are established. So let me begin right away. The technologies that we looked at, as Ron mentioned, include combined heat and power plants with carbon capture and sequestration, crackers that are fueled by hydrogen. While we provided cost estimates, those cost estimates need to be validated, and the way to validate them is through full-scale, real-world demonstration projects. And I've developed the rationale for this in other papers very broadly, but these demonstration projects are meant to provide confidence to follow on projects beyond the demonstration projects that will be fully funded by the private sector. And there's money available now, both through the Infrastructure Act that passed last year and the Reconciliation Bill, the Inflation Reduction Act that passed this year. There's a substantial amount of money for industrial demonstration projects. And some of that could go to chemical industry technologies of the sort that we've talked about. So I think that's an immediate priority. We're really ready to take that step. And I think DOE, which administers those funds, is also ready. The second thing that is in the short term, perhaps not immediately, but in this decade for sure, is to build out the infrastructure. As Ron mentioned, the technologies that we looked at, carbon capture and sequestration and hydrogen, both need pipeline infrastructures. In the case of carbon capture and sequestration, there's also the sequestration piece to put all that carbon dioxide underground. And we just assume that the infrastructure will be there. Our study is not comprehensive. It is not a life cycle assessment of these technologies, so there are costs that are omitted. But the cost of building this infrastructure, isn't really certain yet. There is funding as well in the bills that I mentioned to fund the infrastructure, but it's going to take a while, and there are some additional steps, notably permitting, that need to be carried out before those things can be built. And that could be a real handicap, and as we've seen, the recent debate led by Senator Manchin around this, and we should expect Congress to return to that question, if not in this Congress, in the next Congress. Looking a little bit further out, once the technologies have been demonstrated, there still may be barriers for adopters in the private sector. We've seen this in the solar power sector. We've seen this in wind power. So it's very helpful to have tax incentives for those early adopters to establish the credibility of the technology and to continue to build the scale to reduce the costs. The way we've done that typically in this country is through investment and production tax credits. And those tools could be used in the chemical industry, the PVC value chain in particular as well. In the case of CCS, it's a very capital intensive technology, so investment tax credits may be the most sensible approach. In the case of hydrogen fuel, so the use of hydrogen to create heat, that's a operations intensive. The expenses are concentrated in the operations cost of hydrogen, so there the production tax credit may make more sense. And in fact, there is a PTC for hydrogen included in the Inflation Reduction Act. Another thing that we've learned from past sectors where these kinds of tax credits have been used is that the design is really important. The effectiveness really varies. So the devil is in the details here. And the Internal Revenue Service, the Treasury, is in the process of thinking through how the tax credits in the Inflation Reduction Act are going to work. And the same kind of attention would be needed if we want to jumpstart adoption of these technologies that we talk about in the study. It's also worth mentioning that there are a lot of other ways to achieve early adoption. So, for example, the contract for differences approach, which is being explored in Europe. So we're not wedded to the tax credits, but that is typically the way the U.S. has gone about early adoption. A second tool for early adoption, which is also widely discussed these days, is so-called clean procurement. As Ron mentioned, the green premium for PVC is pretty small. That means that perhaps we could find buyers who are willing to pay that extra price, and the government could be one of those. So this is the approach that's being followed for a number of materials used in construction now, and PVC is widely used in construction, and the public sector is a major force in the construction industry, and it will be more so, especially as this infrastructure rolls out. But there are a number of challenges with this. The one that I wanted to highlight again is one that Ron mentioned. Ethylene crackers produce products for a number of different value chains. So the green premium is only going to pick up that share of production that goes to PVC. And that means the rest of that extra cost for the capital facility to create the ethylene isn't paid for by that green premium. So that's a complexity that's, I think, unique to this industry, and it really differentiates it from some others. So as that procurement discussion goes forward, again, the devil is going to be in the details in thinking about how to implement that. Then a little further down the road, once these technologies may have been established, demonstrated, early adopters have been willing to pay the extra cost, then it needs to be adopted widely in the industry. And there are a couple of ways to do that. As I mentioned in the modeling, we use carbon pricing, and it's a very attractive approach for this sector because it's so complicated, because there are many stages to the value chain, because there are a variety of different technology options. It's a technology neutral approach that allows each stage of the value chain to pay its fair share. However, as I'm sure most of the viewers of this webinar know, carbon pricing hasn't been particularly popular in the US. So I think we ought to be thinking about other alternatives when we get to this point. And the most obvious one is air pollution regulation. So the US has tended to use point source regulation rather than pricing, or some combination of those two to drive adoption, for instance, of pollution control technologies in the power sector. In our value chain, the biggest point sources are cracker furnaces, where ethylene is made, and the combined heat and power plants. That's what CHP stands for. And so if the EPA decided to try to exercise its authority through the Clean Air Act, it's likely that those would be the targets. Whether CCS or hydrogen fuel would be could serve as the basis for a pollution standard is unclear, and we can go into that further in the questions if people are interested in. That's a pretty complicated legal question right now, as I understand it. And then the final piece of the puzzle will be the trade piece. As Ron mentioned, the United States is a leading exporter of PVC. If our domestic producers have to pay a higher cost, then that could put them at a global disadvantage. And the solution to that could be some kind of border adjustment fee and export incentive program to try to level the playing field. But for many of the same reasons that green procurement is complicated. So are carbon border adjustments. And we're starting to get into that discussion in other industries with the European Union at the moment. So with that, I just want to highlight that this is a first step. As Ron mentioned, we'd love to see this work replicated in other value chains, add more technologies, analyze these policy options in more detail. And with that, let me thank you for listening, and I will turn it over to Henry.
Henry, I think you're muted as well.
I followed in David's footsteps here. Hi, thanks for having me here. As Ron pointed out, there are a number of technologies that he examined that can be where you can understand the costs and which we know can be implemented in the near term. And there are a number of other technologies which are more uncertain, but some of which have enormous potential payout. And the ones that we explored are three: the use of biomass, primarily non-food biomass like wood and grass, the use of plastic waste, and the direct production of plastics and other chemicals from water and CO2. And of these, I'm going to try to make the case that the direct production avenue is one which is probably least understood and probably the most important and really merits a focused new program. But if you take a look at the complexity of plastics, it is seldom possible to really get an overview of the life cycle emissions of plastics. And obviously, there are three big parts. Right now, plastics are made almost entirely from fossil fuels. So you're having to produce the gas or in the case of Europe, the oil to produce the raw materials. And then you have to convert it into a useful product. And that's, of course, where the study of the production process we just heard in detail. One of the things that you realize in looking at this is that presently about 60% of the fossil fuels used in plastics actually ends up embodied in the plastics themselves. And that fraction, of course, will go up as the production process gets more efficient. So the fossil carbon that's in the plastic ends up somewhere in the environment. And there, it's been a kind of a complicated analysis focusing primarily on the short-term impacts of discarded plastics on health, on oceans, and in other factors. But of course, in the long term, the carbon that is in these products ends up getting back into the atmosphere. It's so the life cycle analysis here, it can be has a lot of unknowns. Now, I could go into depth on the fascinating technologies available for biomass and plastics recycling, but I think they both have limits for the future of plastic production. In the case of biomass, there's a lot of competition for biomass, and in particular, there are lots of transportation uses for places that are hard to electrify, like aircraft. And there, of course, are environmental impacts associated with the production, transportation, and processing of lots of biomass. In the case of plastics, what we know about the lifetime of plastics is actually quite miserable. We know that plastics in the environment can last from years to, in the case of PVC, maybe even millennium. But the process depends on the type of plastic, where it's discarded. Is it in the ocean? Is it on the land? But we know that in the US, only a small fraction of this material actually ends up getting into a recycling stream. Now, most of the processes now used for recycling plastics are gasification or pyrolyzation, which means heating them to high temperatures. And That's better than incinerating them, just burning it, but it reduces, the technologies available are far from 100% efficient. They can reduce emissions by 25 to 50%. There are some game changers. There are chemical processes for taking plastics apart and producing materials that are identical in properties. And of course, if the plastic is itself made without fossil carbon, then you have much less concern about its eventual greenhouse gas effects when it's discarded. Of course, the immediate effect of microplastics and other problems associated with plastic disposal will still apply. So I wanted to focus on the home run, which is basically doing what plants have been able to do for 1 billion years, that is to take CO2 and water and make complicated organic chemicals. And they do this obviously at room temperature, but they don't do it terribly efficiently. The average is probably less than 1% efficient of converting the energy in sunlight into the energy stored in a carbohydrate or the materials that the plant synthesizes. And the process is basically to take the oxygen off of water and take the oxygen off of carbon dioxide and combine them to make these organics. So the issue is, can we do this synthetically at a much higher efficiency? And half of the problem is being attacked because we're trying to figure out how to take water apart, primarily through electrolysis, but through other means, through a national hydrogen initiative that is focusing particularly on electrochemical cells that are electrolyzing water. Now, it turns out that the same general approach can be used to take CO2 apart in cells. And so there's an opportunity to both separate the hydrogen in one process and the CO2 in another, and then combine them using well-known chemical processes. Or you can go for a single device, a single electrochemical device that can do both processes and actually take in CO2 and water and produce directly chemicals like ethylene and other products that can be going into petrochemical production. The ultimate, of course, is not to use electricity to drive this process, but to use sunlight, thereby making this a completely artificial photosynthetic approach. The limitations on this are most of the current experiments which are underway have to use concentrated CO2, which of course is available from lots of sources like cement plants and ethanol facilities. But the process of actually capturing the CO2 in low concentrations from air is a significant hurdle. And the technique, quickly illustrated here, is basically to reproduce synthetically the processes that plants use to do the water separation and the CO2 concentration. The interesting thing is the first step in this is in the natural photosynthesis is hydrogen production, which is what takes a lot of energy and happens in the sunlight. There are a number of different facilities that are producing lab scale and even somewhat larger scale demonstrations of devices that can perform these separations, typically in separate processes for the water and the CO2. Now, these challenges have been taken up in earnest by the Europeans, primarily because the cost of fossil fuels is much higher in Europe, particularly natural gas. And of course, with recent events, the price of natural gas has just gone through the roof. So they have a number of very aggressive programs that are at demonstration scales to perform many of these explore many of the technologies I've just discussed. And in fact, they have actually set a goal of trying to find petrochemical production from sustainable non-fossil sources. We, of course, have nothing approaching this. On the other hand, the U.S. has huge comparative advantages in this area. It's a place where we should be able to excel, given the right incentives, because the kinds of things you're doing to make these electrochemical and other devices work are based on sophisticated computer simulations, artificial intelligence, advanced manufacturing, advanced biological processing. We're extremely good at this. What we haven't done is applied a lot of this work in earnest to this petrochemical challenge. The interesting thing about these technologies is that most of them are modular, or the large facilities are scaled up versions of smaller components. And that means that you can actually do quick learning by trying things, testing them, doing simulations, and then trying again. So the ability here to get on a steep learning curve through fast learning is certainly possible. And the modularity of the fact that some of these systems are going to be able to operate at relatively modest scale, say the size of a current ethanol plant, means that you could, in principle, locate these production facilities in many parts of the country, depending on whether you have cheap electricity, and water, which are the two main inputs. So the question then is, what do we do about it? David has outlined in the broad strategies that you need to move a technology from a laboratory or advanced, early demonstration phase into commercial production as quickly as possible. One thing in this area that it seems apparent is that the ability to take CO2 and water and turn it into a petrochemical through a highly efficient process driven by electricity or sunlight is so important that I would argue it deserves a place on the Earthshot radar of with a goal similar to what the Europeans are setting. This is clearly a major home run. And the second thing we need is the ability to understand the life cycle environmental impact of alternative production and disposal of plastics. So thank you.
Thanks so much, Henry, and to Ron and David as well for their presentations. Next, we're going to hear some comments on these presentations and how they impact industry and communities. So first, we're going to hear from Brett Perlman. He is CEO of the Center for Houston's Future, a nonprofit organization that focuses on matters of long-term interest to the Houston and Gulf Coast region. Prior to joining the center, he worked in senior positions in business and government, as well as the nonprofit sector, and he holds a degree in public policy and law. And after Brett, we will be hearing from Dom DeCaria, Vice President of Regulatory and Technical Affairs at the Vinyl Institute, a trade association for an important segment of the chemical industry. He has spent his career in the steel and plastics industries, and he was trained as a chemical engineer. And I'll remind the audience as well that we'll be opening to audience Q&A after we hear from Brett and Dom. So please type your questions into the Slido box, which should be below the stream here. So I'll invite Brett to come on first and to hear your comments.
Thanks very much, Abigail. As Abigail mentioned, I'm Brett Perlman with the Center for Houston's Future. We are a nonprofit that is working to decarbonize the Texas and Gulf Coast region. I want to thank my colleagues, Henry, David, Ron, and Fran Brown for letting me work on this project, and the Mitchell Foundation and Breakthrough Energy for funding it. I wanted to provide a little bit of feedback on things that I learned along the way from doing this work. So I think there are a couple major takeaways that are very important from what has been presented today. The first is that getting this right in Texas is key. We are a large emitter of carbon dioxide along the Texas Gulf Coast, but also very key to solving this problem. And so if we can get this right in Texas, we can take these learnings and really spread them around the globe. And that's some of the work we're trying to do at the Center for Houston's Future. The second insight, I think, is that the foundational steps to decarbonize the petrochemical industry have become very clear through this study. And I think David or Ron referred to these as clustering effects, that you get most of your bang for the buck by simply looking at the big pieces of the value chain that are the key emitters. And in this case, they are the crackers and the CHP units or cogen units that are part of the process. And so surprisingly, by focusing on those sectors of the value chain, you get most bang for your buck, not only in the sector that we studied, which is the petrochemical value chain, but really across the entire plastics industry. And so I think there are huge opportunities to basically decarbonize, and that's the learning from this, to decarbonize the entire plastics sector by focusing on those high emitting sources. The third, I think, takeaway from this is it's clear what the technology pathways are to do this. CCUS and hydrogen are both of those, two of those pathways, although the one that Henry just mentioned in terms of some of the research that could come after this, I think is important too. We are in the process at the Center for Houston's Future in looking at the hydrogen pathway in particular through the funding opportunity announcement that the Department of Energy has just released for hydrogen hubs. And we expect that this work that Breakthrough and the Mitchell Foundation have been funding will be very influential in our application in trying to address the decarbonization in the petrochemical industry. And then finally, I think the last point that needs to be taken from this work, and one that can't be, is I think a big important point, is that the cost of doing this is not that high. The green premium for decarbonizing the petrochemical industry under this work is between 5 and 14%. And so we are working with end-use customers throughout these value chains and working with Mission Possible Project and the World Economic Forum to bring those early adopters to market. And then finally, I think these other tools, such as being used in Europe, such as the contract for differences, or perhaps the idea of clean procurement, are also tools that need to be used in order to achieve the goals we're looking at. So I take away from this entire study that this is a very doable thing, and that we in the Texas Gulf Coast really need to be a key part of this project in terms of thinking about how we decarbonize not only the PVC value chain, but the entire petrochemical industry. So thank you very much for letting me participate in this study and to be part of what I thought was a very exciting and interesting effort.
Dom, I think.
I got you. Yep. It took me just a second there. So as Abigail mentioned, I'm Don Bucari. I'm with the Vinyl Institute. The VI is the trade association which represents the PVC resin, additive, and compound manufacturers in the United States. At the VI, we want to thank Ron and David for the opportunity to participate in the review of this work, and also to Abigail and to Breakthrough Energy for funding it. As many know, PVC is already the low carbon intense material of choice in many of the applications where it's commonly used, including water and power infrastructure, irrigation, and other agricultural applications, building envelopes, and more. And so while we already have a good story to tell relative to other materials used in these applications, we're also focused on driving improvements in the industry's carbon footprint to help the federal government decarbonize its massive investment in infrastructure going forward. So we learned quite a bit from this process, as much as we have from the final report itself. By engaging with the research team early on and understanding what the work would seek to understand, we've developed a more nuanced approach to how we are looking at our own industry initiatives. For the benefit of the audience watching this webinar, the Vinyl Institute has spent decades in a mode of continual improvement, and in 2015, we formed the Vinyl Sustainability Council as a result of a third-party materiality analysis of the industry. That study revealed the need for industry to focus on three main areas of improvement that would drive industry sustainability forward. Those impact areas are resource efficiency, including recycling, emissions reduction, which includes emissions to air as well as water, and also health and safety, which is around user and community health. And our emissions reduction task force has engaged with NGOs like Building Transparency to help develop categories for their embodied carbon and construction calculator tool. And we've also been advocating for the use of recycled content in order to drive embodied carbon lower in durable PVC products. So a little over a year ago, the task force identified the need to develop our own deep decarbonization roadmap, and we began to develop a scope of work for resin production, which will be completed by the end of 2022. And it was right after we started that work that we got the phone call from Ron asking for an initial conversation about chemical industry decarbonization and the role the vinyl industry could play as a case study in that regard. And so here we are a year later. We're completely thrilled to be able to participate in this today. So the bulk of the greenhouse gas impact for PVC resin production is from the raw material extraction life cycle phase. And we're glad to support the work from ITIF to identify technologies and policies to support the reduction of carbon intensity of that phase. Our industry members would be very interested in working with policymakers to find ways of de-risking industry's investment in these new and novel technologies. So keeping in mind that the industry is already the low carbon intense alternative in many applications, what policymakers should also consider is how to enable the industry to invest in a near zero carbon future. At the moment, the industry is limited in its ability to invest because we're lacking regulatory certainty, especially with respect to the PVC Act, which has been stuck for years in a rulemaking step. Without this regulatory certainty, our industry can't make the sort of major investments in low carbon intense materials and processes that we're driving toward. But nonetheless, we continue to work on what we can within our own facilities, whether it's electrification or fuel switching of boilers, and further investments in localized power, which can also improve resiliency. So overall, the findings and the strategies that are identified through the study have been highly interesting. We are absolutely thrilled to see these results and take some next steps as well. And so looking forward to working with the research team and also with Abigail and looking for opportunities to connect to possible funding sources and other policy discussions later on, and also looking forward to further work from Henry on the technology development as well. So thank you again for this opportunity, and we really appreciate it.
Thanks so much, Dom and Brett, for your thoughts. And now we're going to go into our panel Q&A. Again, reminder for the audience, if you have any questions, please submit that through the Slido box. Really great to hear the presentations and the comments. And I think something that a lot of folks are thinking about are the recently passed bills and the implementation of those bills. And it's great to see how some of those programs may already be important for this industry and for the technologies that were identified today. I'd love to dive a little deeper on that. So we've heard, from David that some of the tax credits that were in the recent IRA package, may be relevant here for potentially both CCS and hydrogen. Brett mentioned the hubs and hydrogen hubs as part of the infrastructure bill, and the importance there. Maybe mention also there's DAC hub funding. And so, the combination potentially of those two things going into what Henry was speaking more on that kind of game-changing technology. One question I have is, in the studies that you completed, are there lessons learned for how to target the current demonstration and other funding to specific, locations or facilities? Are there ones that you have found through, your work that, may be ripe for those first and of a kind demonstrations that, these bills have unlocked? Maybe I'll start with Ron, and then we'll see who else may have some thoughts there.
Oh, well, thanks, Abigail. That's a loaded question. If you look at the work we've done, there's clearly a range of facilities and sites within the PVC chain, which is all we looked at, which are the largest emitters and the smallest emitters. And if you look at our studies as well and look at the cost curves that we have in the study, you'll see that some of them are isolated sites, some of them are integrated sites, and you can also see that some of them are more appropriate for hydrogen implementation than for carbon capture. So I think that you could take our results of the study and sort of rank order as the cost curves do, which sites might be best for hydrogen and which might be best for carbon capture. Those are the two studies those are the two technologies we studied in depth. Does that answer the question?
Yeah, thanks, Ron. Any of the other speakers want to jump in on this? David?
I guess I just do want to make sure that I don't know that we covered this, but the vast majority of the facilities in this study were in the Gulf Coast region, so in Brett's area and up the coast towards New Orleans. So I think that's obviously the place to begin with. They also have some of the transportation infrastructure, that is pipelines, for some of these technologies. And just to come back to your original question, Abigail, I think that the thing that, so first of all, the three bills that passed over the last year are very powerful set of programs and tax incentives to push these technologies along. And as we were working on it, I think we thought CCS was closer to maturity, but it's possible that the incentives in the bill will sort of jump hydrogen ahead of it. And Brett can comment more on that since he's working directly on it. But it's very exciting to think that our ideas could get into actual proposals to build stuff. It makes me a little afraid, as I mentioned. It is the first of its kind, and it's not a full life cycle analysis. But if it can provide some guidance to thinking about it, that would be a great outcome.
I would say, Abigail, that it's really helped to target our work on our hydrogen hub proposal. And so looking at high heat applications, particularly in crackers in the petrochemical value chain, as well as cogen units, are two places where we're looking to include projects in the Gulf Coast region. And I'll just consider this webinar an advertisement. If you want to participate with us in a project like that, come see me, because we would love to have you be part of this. On the CCUS side, I know that there are already projects that DOE has funded, a Shell project in particular, that is looking at decarbonization, of a cogen using carbon capture. And so some of this work will hopefully support some of those efforts along the way. So I think there are real practical implications of what we're doing, and that we're going to try to take the work that has been done and try to start to move forward so we can have real first of a kind projects that we can implement along the Texas Gulf Coast.
That's great. Let's turn to some of our audience questions here. One question is on kind of motivating young people to kind of work in this field. Can any of you speak to leveraging interest in decarbonization in order to do this? Dom, it sounds like you may be working on this.
Yeah, just in general, first of all, I think the industry is always looking for better ways to, engage, younger people, to try to bring in good talent, try to bring in people for the right reasons, to understand like, hey, we're working on sustainable solutions for what we do, and this is an opportunity to use your skills and talents to be able to help our industry do that. It's a complex issue, right? Like in a lot of ways, chemical engineering in and of itself is just a matter of getting more efficient chemical process, which, reduces energy usage and reduces, waste and whatever else. And just that process of efficiency is kind of built into the discipline. But I think it's about storytelling in a lot of ways, and making sure that we're that motivation piece is about how do we get out there with our message a little bit more clearly. It takes studies like this, it takes studies like the other one that we're working on, and then promoting it and talking about, this is our plan, this is what we're doing, and preaching that when we do go out to universities and we talk about, hey, what is a chemical engineer? Or we go to high schools and we want to advocate for why to get into a discipline in the first place. So we're going to need these types of studies and be able to compact them in a more simple fashion to be able to use that to motivate kids. There's another aspect of this too, which is about, the energy water nexus, right? Because, on all this discussion around energy and carbon impacts, you can't forget that, there's a substantial amount of energy that's used to just move water around the country. So as we think about water reuse, and as we think about some of the other environmental impacts that are part of industry, but are also just part of society, I feel like we can use conversations like this and use that as a means of, and also bring in the water conversation, which a lot of times people are a little bit more triggered by, and be able to say, hey, look, there's real implications that you can have by being a process engineer and by working on decarbonization initiatives from the time that you start your career out, and then you can have a long-lasting career to continue to do these things. So there's definitely opportunities.
I guess one thing I would say is that we had a session in this year's meeting of the American Physical Society, which is a conflab of physicists they have every year. And we had enormous turnout of young people on the artificial photosynthesis project seminars. And the speakers emphasized the fact that they're trying to get people with a variety of skills to understand how their skill would be relevant to these interesting electrochemical problems. And it's a combination of often people who have skills in biology and materials science, and as well as conventional chemical engineering, artificial intelligence, just to expose the kinds of questions that are on the table to a broad set of talented people is really important. And I think our one experiment at our annual meeting this year was there's a lot of interest of young people out there.
Well, that's great to hear, Henry, and great to hear what you all are already doing at the Vinyl Institute, Dom. I think we have time for maybe one or two more questions. I have a question here on ways to accurately measure, report, and verify carbon sequestration tools used to generate carbon credits. And I think maybe broadening the question to just the importance of being able to, do a proper life cycle analysis to ensure, the emissions reductions in these technological processes, and then being able to attribute that to, the lower embodied carbon product and, get, value out of that. Is there anyone who wants to try and cover kind of what's in the works now, what still needs to be done to improve this space?
Well, I will take a crack at it. I can only say there's an enormous amount going on in this area. It's a very challenging area. I do think the right questions are being raised about the durability of carbon offsets and carbon credits. This is why we need, serious demonstration projects that produce knowledge that's broadly shared, so the public can gain confidence. I think we've seen with some carbon credits that they don't necessarily last, and so we're going to need a comprehensive system. I was at a meeting actually that Abigail's organization sponsored, and somebody made the comment, we need to go slow now so we can go fast later. I think this is an area that we have to get it right. It's going to take a while to sort it out. But if we do, it's going to enable, it's really a platform technology that's going to enable everything else. So I would say, watch this space. I think there's a lot of energy going into it. There is a question in my mind about what's the proper time for the government to sort of step in and consolidate it. And I think it's something that really bears close watching.
It's a great point, David. And I think your work on identifying sequestration specifically in here it's valuable. I also wanted to highlight that we've been working with NIST on a separate project just to even look at not necessarily sequestration, but just carbon savings. In this, we've talked before about having a kind of a qualified way of reducing carbon impact in products is through the use of recycled content, for example, right? Which I realized was out of the scope of this study, but as it goes forward, looking at where should the carbon savings be allocated to in terms of recycling as one I guess one activity. It's important for us to see it's not just about who's using it, who's using these materials to be able to claim everything, when it's really making the materials available in the first place is part of that equation. So I would say the same thing for the sequestration. There may be allocation of who's benefiting from it, who's actually making the investment and providing it. There's got to be a way to look at that equation. And I'm sure different organizations, NIST being one of them. Obviously, there's more research to be done. There's certainly a lot of people that are focused on it right now. So it's exciting to see what's coming.
That's great. I think we're really coming up on the hour, so I'll take this chance to wrap up to thank again our speakers, Ron, David, Henry, for your presentations. Encourage the audience to go take a closer look at those studies and to look out for Henry's once that is published as well. And then thank you, of course, to Brett and Dom for your participation in this work and your comments during the webinar. I think it shows there's a lot of excitement in the space, a lot of opportunity for decarbonization in this industry, both with maturing technologies that are out there that can take advantage of some of the recent funding opportunities out there, as well as some game-changing technologies that Henry has been exploring. So again, thanks everyone for joining us today, and look forward to working together on this issue in the future.